How you doing?
Should we just run in front of the camera?
Yeah, just run in front of the camera.
Please.
You know, give a short history of your life, you know, and what your purposes in life are, and what your goals are.
Jessica. I'm Taylor over here.
I'll tell you, you gotta give me a face.
Yeah.
There we go.
All right. So now you don't want to put it on me. You want to put it on the board. Unless Val just wants to look at me all night. Hi, Val.
You know that's what Val wants.
Stop it, all of you.
Okay, so guys, there's going to be one small little problem here. It turns out that I'm out of paper, so I have to backtrack and conserve a little bit and use some of the other one because the back sides also used up.
You know, the spaces, I've seen lots of white space
Here we go.
on these papers.
Yeah, exactly. We're going to utilize the white space. Okay, so here we go. The name of the game is Ionic Compounds, and Ionic Compounds are compounds created by members of two opposite cliques, two opposite groups, two opposite points of the spectrum. So, can anybody tell me, bird's eye view, long picture from the very top, what the periodic table is divided into?
Bring me a pen.
No, I'll bring it in.
We know there's these little stair steps, right? Do we really care? So somebody better make sure that that camera is pointed on the board.
Oh, it is.
Is it?
Yes.
It looks like it's pointed over here.
It gets both. It has.
Oh, you can see it. Okay.
Yes.
It's got wide angle. All right, good. So let's wait till Cal comes back. While we're waiting.
I burned myself with. Oh, that's why the pen's not working. Cool. Have you ever burned one of those before? No. Looks pretty cool pens.
Eat up, my good man. Did you want me to bring you any some of the... There you go. I settled that bitch.
Thanks, Cal.
Okay. So, two things. What are the two things? What's up here?
Non-metals and metals.
Exactly. So up here, we got the non-metals in blue. And over here, all these people, all the way over here, are called the metals. So we got the reds and we got the blues. So when we talk about ionic compounds, an ionic compound is simply a red and a blue mixed together. So we get the red and the blues. What do we get? Ionic compounds. A metal plus a non-metal gets you an ionic compound. So for example, let's take lithium and let's take fluorine. Lithium's in red and fluorine's in blue because it's a non-metal. So what kind of compound are they going to make?
An ionic compound.
Right. Now the only question is it one lithium to one fluorine, or two lithiums to one fluorine, or two fluorines to one lithium, or 2 to 3, or 3 to 2? How do we know? This is the big question for ionic compounds, the proportions. And there's a real easy way to figure out how to set these things up and see which is going to go to which. I'm going to do the long way first, and then I'll show you the short way. So here's the long way. The long way is to figure out what the electron configurations are. So we know fluorine has a 1s2, 2s2, 2p what? You guys tell me.
2p6. Or lithium.
Fluorine's a 2p, anybody know?
5.
5.
It's a noble gas.
Good call, guys. It's not a noble gas yet, right? That would be a...
not a noble gas.
If it was 2p6, it would be a noble gas.
halogen.
Yeah, it's a halogen, exactly.
Yes.
And what's lithium? Lithium's a 1s2, 2s1.
Or an alkali metal.
Or an alkali. Now, does lithium want to keep this outside electron, this lonely electron in its outside shell?
No.
No.
No. Does fluorine desperately want an electron to become whole?
Yes.
So lithium has one electron to get rid of, and fluorine has the need for one electron. So it's a marriage made in heaven, isn't it? Match made in heaven. This guy gives up his electron to, guess who? Fluorine. Now when you give up or lose an electron, you become positive or negative?
Positive.
So lithium becomes +1, And fluorine, when it gains an electron, does it become positive or negative?
Negative.
So it becomes -1, and you see how the positive and the negative cancel. And we end up with just LiF. Okay? So that's doing it the long way with electron configurations. The short way is just to know that lithium is a +1 and fluorine is a -1, and if the charges match, you can just cancel them. You know it's going to be LiF. Now how do we know that lithium is going to be +1 and fluorine is going to be -1 all the time without going through all the gyrations of doing electron configurations?
Because all the halogens are always -1.
Exactly, all the halogens. So anything in the halogen column is going to be a -1. Anything in the alkali column is going to be a +1. What about the second column?
+2.
+2. Do we see a pattern developing?
Oh yeah.
Jump across the bridge, don't get wet. What's the third column going to be? Hint, third column going to be?
+3.
+3. And the fourth one is going to be +4. Now, the next column over, that was boron, that was carbon. The next one is nitrogen. So just to show you something important about nitrogen, it's a 1s2, 2s2, 2p, 3. You guys remember how to get this?
Yeah.
Okay. Does it want to lose 5 or gain 3?
Gain 3.
So if it's going to gain 3, what's its charge going to be?
-3.
Exactly. So we go from +4 to -3 for the nitrogen column. And then what's next is
-2.
-2 and then -1. So I didn't draw it very well up here, but you can see it goes +1, +2, +3, +4, -3, -2, -1, 0. Is everybody okay?
Yes.
And that makes life a lot easier than having to do electron configurations to match the nonmetals with the metals. And it leads us into the basic technique for this chapter, which is called flip-flop and drop. And here's what it looks like.
Never say that out loud to a teacher.
No, don't. Shh, this is a special private technique.
How did she know? Wait, is there a -2 between the -3 and -1?
Yes,
Yes, okay.
it's oxygen.
Dirty
I didn't have enough room up there to put it in. I don't want to like spend more time
Yes.
because I don't have much white space left. But so if I'm going to say, let's say we're going to put Mg together with Cl.
So that's a +2 and a -1.
Exactly, it's a +2 and a -1, which means magnesium has 2 electrons in its outermost shell. It doesn't want them, it wants to get rid of them. Chlorine, like fluorine, is 1 away from nobility, right? But chlorine doesn't want 2, does it? It wants 1. And magnesium wants to get rid of 2, so if he just has 1 chlorine, it's like, well, he's still got 1 left, and he's not like a happy camper, right?
Yeah.
So you really like to have 2 chlorines to pass them off to, right? But instead of showing that with long electron configurations and showing arrows, showing electrons going here and there, you can just do this, flip, flop, and drop. So when you flip, flop, and drop, you don't drop or flop the plus or the minus, just the numbers. So this one comes over here, that's a flip. This one comes over here, that's a flop. And then you drop. So you end up with MgCl2. The 1 is trivial. If you want, you can say Mg1 Cl2, but you don't really need to specify it. So that's how you get your ionic compounds the quick, easy, and no muss, no fuss way. Now she's probably going to want you to show like valence electrons and arrows and electron configurations and all that kind of noisy, busy legwork kind of stuff that you don't really need to know as long as it was taught correctly to you, so you understand why the charges are what they are up here. You don't need to go through all those gyrations, but she may ask you to show your work at some point, so just follow her technique when she shows it to you on the board. Has she done this yet?
Yeah, but we didn't do it with electron configuration.
What did you do it with? Valence electrons?
She was just like most common denominator.
Yeah,
Yeah.
that was it.
She's like lowest common denominator, and you like have to make the charge equal or neutral.
But where do you get the lowest common denominator?
Made it up. She just made it up. I don't know.
All right, well,
So don't pay attention in class.
all right, well, fine. If she doesn't, then just flip-flop them, drop them. So here we go. Here's a hard one. Aluminum oxide. Now, she's going to write them out like this. She'll write them out longhand. And one thing you need to know is that this is really oxygen, but it ends oxide. How come? Because the ending of all these ionic compounds the first set we're looking at are called binary compounds, because there's one of each type of atom represented. One aluminum, for example, one oxygen, one mag, one chlorine, one type. Up here, there's two chlorines, but there's one type of element, chlorine, and another second type of element, magnesium. So there's two types of elements represented, two being bi. So these are called binary compounds. Test question alert, binary compounds end in?
Ide.
Ide. Test question alert, binary compounds end in?
Ide.
Ide. All right, so this is really oxygen, but because it's a binary compound, it ends in ide.
Ide.
So you say, okay, we got aluminum, that's Al, and we got oxygen, hidden by the ide, but it's still there. And what's our charge under oxygen?
-2.
And what's our charge on aluminum, which is under
3.
boron? And Jessica's writing the numbers there. And so flip, flop, and drop them. What do you get?
Al2O3.
End of story. So we get Al2O3, flip, flop, don't forget to drop, because the charges disappear when the ions come together. The charges hold the ions together, and the charges motivate the elements which have ionic forms to come together and stay stuck. But once they stay stuck, the charges apparently disappear. They're still there below the scenes, you can't see them, but it's neutral from the outside. So Al2O3 is aluminum oxide. So once you've seen that, then you can get all the binary compounds pretty easily. So let's do one more. Let's say we've got sodium sulfide. Sodium sulfide.
+1.
So we know sodium is +1, and we know the I just means it's a binary compound, right? So it's really what?
-2.
It's really sulfur. -2, and Cal, what do we get?
Na2S1.
Or just Na2S. Okay, so that's the way we're making all these compounds. We have a red and a blue, a metal and a non-metal. And when I put a red and a blue together, I get an ionic compound. And the reason they're called ionic compounds is because the motivating force for them to come together is that each of these forms a little ion to get like a noble gas electron configuration, and then they stick together because opposites attract. So, at this point, you should be asking yourself one question, or two questions actually. So if you understand the basic premise, which you do, then why don't you wonder about other possible combinations? I showed you a red and blue combination, right? What other possible combinations do we have?
A non-metal.
Yeah, what about this? Could I have a BF3? If I did that, it would be blue, blue, right? The thing about blue blues is they exist, but not until next chapter. So next chapter we'll deal with blue blues, the non-metal compounds. They're called covalent compounds. This chapter all we care about is the red blues, which are called ionic compounds. So one final question, what about the
Blue.
the next chapter? What about the
Reds.
red reds?
Oh, right.
Right. Now think about the blue blues. The blues want to get electrons, correct? So they're gaining electrons. So if both members of the bond are gaining electrons, they could conceivably share them, couldn't they? They're both getting something, so they could share them. So that's why the blue blues will work, because they actually end up sharing the electrons that both of them gather. These guys, however, are doing what? Are they gaining or giving?
Trying to give.
They're trying to give their electrons away, right? So if I have two metals and they're both giving away electrons, there's nothing there to share, right? So there's no way that they can both like give electrons away and form a bond because they have nothing to bring to the table in the arrangement, right? So that's why there's no metal-metal bond. Test question alert. There is no such thing as a metal-metal bond. In other words, I can't have two metals together. I can't have sodium, iron. Sodium's a metal, iron's a metal, can't do it. I can't have magnesium, copper. Magnesium's a metal, copper's a metal, I can't do it. Okay?
What about the metals underneath?
Nice. But what about the metals themselves? The metals themselves are a special case. They're very boring. For example, iron is a metal, and it forms this kind of situation. It has an atom of iron next to an atom of iron, next to an atom of iron, next to an atom of iron, next to an atom of iron. In other words, it's a clone of itself over and over and over and over again. So a metal really is just the same atom over and over and over again. So when you say a metal bond, you're really talking about something very, very homogeneous and boring and uninteresting, because it's the same atom connected to the same atom, connected to the same atom, connected to the same atom. So it's a special kind of bond called a metal bond, but it's like all the same atoms. So it's kind of not very interesting in terms of chemical reactivity. So it does exist, but it's a special kind of bond where it's just the same atom over and over and over again. We're more concerned with dynamic, kind of like genetically linked bonds, where you have like different things bringing different qualities to the table when they meet. Just like the gene pools separate, bring different characteristics and qualities together when they offspring is produced. So it's a more interesting world that way. So for that kind of world, there's two compounds that are really important. Ionic Compounds, Chapter 5, which are metal, non-metal, and Covalent Compounds, Chapter 6, which are non-metal, non-metals. Okay? So back to the races. We'll just focus on 5 for this session today, and just do the ionic bonds. So we got a pretty good idea of the binary ionic compounds. Binary means two different types of elements are represented. We could have multiple units of the same element, but two different types. Everybody cool with that? So even there's 5... What?
I'm sorry, I kind of just jumped out the window.
It's Halloween.
That's creepy.
So is it okay that we have 5 atoms here?
What? Oh, yeah.
But it's still a binary compound?
Yeah, because there's two things.
Yes. All right, good. So you got that, Val? Don't listen to a gal. He's like this kind of like smoking crack over here in the corner.
He's so giddy.
That was so funny. Just look at what? Oh, son. Oh, God.
Water break.
It like hurt you.
I'm gonna go check it out and see if it's still alive. Just like now. That'd be stupid.
Oh my god.
Okay, next subject. What if we have, like, not just 2 types of elements, but
Polyatomic.
3 types of elements? Okay, if these are all Lego parts, if we have a plus on one side and a minus on the other, right? What if we just have like a clump of stuff that makes a minus? What are they called? Jessica knows.
Polyatomic.
Polyatomic ions. So here's a clump of negativity. For example, SO4 neg 2. Here's a cluster or a clique or a little club of nonmetals linked together at the hip. It really looks like this. There's sulfur surrounded by 4 lovely oxygen at all times. Wherever sulfur goes, the 4 oxygen go with him. And the whole little clique has a charge of -2. So instead of just having one nonmetal with a negative charge, you've got a group of nonmetals with a negative charge. What's that group of nonmetals called?
Polyatomic.
Now, aside from the fact that it's a group of nonmetals, the game still remains the same. You can flip, flop, and drop because you have a negative charge with a metal, which is a positive charge, so you can put these together and get bigger types of ionic compounds. So let's say if I put lithium with SO4 neg 2. What kind of compound am I going to have? Ionic compound, and what's the formula going to be?
Li2SO4 in parentheses 1.
But we don't need the 1.
Oh, right.
But nice for the parentheses, because whenever you flop across a poly, you have to parenthesize the poly. But we just have to drop in this case, right? So we get Li2SO4. So the big question becomes, well, how do I know that SO4 neg 2 is a polyatomic ion?
We have this sheet.
And the answer is, there is a prefabricated sheet of these possible polys, and only those possible polys, to play with. Is she going to make you memorize that sheet, or is she going to give you access to
No,
it?
I think we just get access to it.
But she hasn't stated one way or the other? Sometimes teachers are really stupid and expect you to memorize that stuff. So see how it goes. If she makes you memorize it, that's why God gave you forearms, caps, pens, backside of computers, and friends.
And
Were you alluding to cheating?
No. I was alluding to
and
counteracting administrative stupidity.
okay, next time we take a test, you can't move. By the way. Yeah, I mean you got an A. Okay, so you need to sit by me like you always do.
It'll rub off.
Well, sitting by him, he got a C.
No, maybe you didn't look hard enough, Cal.
Okay. So, let's say that we have,
Oh wait, one question.
yeah,
If you have an element like before the SO -2, 4, and when you do the flip flop and drop.
coming up.
Okay, good.
Here we go. So magnesium hydroxide. So, you know magnesium is Mg.
+2.
And you know it's +2 because it's in the second column. And you say hydroxide. Doesn't sound like an element I know. Maybe it's a poly. So you check your poly sheet, and sure enough, it's on there.
Yes, it is.
Where? Oh, OH.
Exactly. It's neg1. So you go OH neg1. How come? Because it's on the sheet like that, right?
Yeah.
And then, are we ready? We can flip flop and drop. So Cal's going to do it. What do we got?
We have M1OH2.
And what do I have to do to the OH?
Parentheses.
Whenever you flop across the poly, parenthesize
Oh yes.
the poly.
Because otherwise you're just putting the 2 by the H.
Exactly. Nice. Good explanation. Otherwise you have MgOH2. This is really MgO2H2 because the 2 distributes to both pieces on the inside. Makes sense, the difference?
Mm-hmm.
So you have to parenthesize the poly. You have to parenthesize the poly. So when you flip, flop, and drop, and you flop across the poly, you got to parenthesize the poly. Everybody cool with that?
Yes, sir.
Okay, so now let's do sodium phosphate. Sodium phosphate.
1.
Oh, big.
Wait, what are we
big
doing?
space.
Sauce? What?
We're doing sodium
Phosphate.
phosphate. You know sodium's a +1 metal, so you put that down.
But
Phos-
which phosphate?
Phosphate you don't know, so you go to your polyatomic ion chart.
Oh, phosphite and phosphate. PO3 negative.
Make what?
Oh, the 4 was on the bottom, but it was negative 3.
PO4, neg 3?
Yeah.
Okay, so Taylor, take it away.
Na3, parentheses, PO4.
Yeah, you don't need them, so you can just say Na3, PO4, and you're done. Question?
All right. Let's just say, like, randomly that Na had a +2 charge.
Yep.
When you
How about we
flip.
change it to beryllium then?
Okay.
So I don't get confused.
Okay.
All right, let's do it. Good point. So we'll do beryllium phosphate.
Oh,
Okay?
Jess, you're so smart.
So, go ahead.
Okay. Now, when you do the flip, flop, and drop,
Yep.
do you multiply the 2 and the 4,
No.
or do you just?
Put it on the inside of the
Just
parentheses. Don't
flip.
deal with it.
And flop. But what happens when you flop across the poly?
What?
What happens when you flop across the poly?
Parentheses,
Parenthesize the poly.
Okay. Okay. So you parenthesize, even though like the 4 is there, you don't do anything with 4.
No.
Excellent.
Because you don't want to get Be3PO42.
All right.
No, that's...
Slightly excessive.
Yeah.
42 O's.
Very, very excellent.
So whenever you flop across the poly, you parenthesize the poly. Parenthesize the poly before you flip, flop, and drop.
Oh, really?
So it's a BE3, parentheses PO4, parentheses 2. Right, Val? Right. Okay.
Excellent.
Got love for you, baby. Okay.
I bet
What up, girlfriend? Right, so
I bet she's laughing right now.
anyway, yeah, she's probably watching the game right now. So eating hot dogs, and is it over yet?
I think it's over and then 1.
Okay.
Getting hit on by ugly old men. Ha! You like that,
They're
Beth?
talking about it on the radio, as I was right here.
Okay. So,
Wait, Giants won?
I think so.
any other question?
Is this the whole chapter?
Yes.
Yeah,
Are you
I can't
joking?
do the stupid D block elements at all
What,
with
no,
the
well,
stupid
yeah,
Roman
well,
numerals.
no problem,
And I just
no
want to
problem.
pee
Yeah,
all over
yeah.
myself.
No,
and it
no,
comes out.
hold it in.
Yeah,
Hold it in.
please, no peeing.
Here's the deal.
All over the leather.
Can we go back to this original chart that I did?
Yes, sir.
What was the key to being able to do flip-flopping and dropping?
No.
And,
I mean,
and
the
knowing the
numbers.
charges at the top of the columns, correct?
Yes.
As long as the charges in the top of the columns, is it tough to flip-flop and drop?
No.
And what if we didn't know the charge at the top of the column because it was polyatomic? We have a little sheet
Sheet.
that tells us what the charge is, right?
Yes.
So we just need one more little handicap kind of helpful aid for the transition metals, which have no top of the column charges.
Okay.
So in the most bizarre possible way, they use Roman numerals to tell you what the charge is for a transition metal, which may have multiple charges, but the only one you care about is the one they tell you about this time. So every time they give you a transition metal, they'll say, this time it's +1, or this time it's +2, or this time it's +3. And how will they tell it to you? By saying +1, +2, +3? No. They'll go Roman numeral 1, or Roman numeral 2, or Roman numeral 3, or 4, or 5, or 6. Okay? And here's how they do it. So, let's say we have lead, 4, phosphate. Actually, I should have written it out like this. Lead, L-E-A-D, Roman numeral 4, phosphate. So, we know lead is what? Pb? If we don't, we just look on the trannies until we find it.
Right?
And what charge does lead have this time?
+4.
Exactly. Roman numerals tell us so. And we know phosphate is PO4 -3. And Taylor's going to do it for us.
Hold on, time.
Huh?
Time out.
Yes, time out. Stop.
PB is under the +4 charge anyway.
No.
It's
There
in
is no
that
positive.
column.
There is no column. There is no charge in the columns for the trannies.
Yes.
There's no charge for the columns for the trannies. There's charges only for the main group elements, the S's and the P's. There's no charge for the groups of the trannies because they have multiple charges. At any given time, they can be +1, +2, +3, +4, +5, +6.
So where's it? So like
So there is no.
underneath aluminum and silicon and phosphorus and sulfate and
Yeah,
sulfur.
those all
they
count. Those all count from this right up here. Minus +3, +4, -3, -2, -1.
But that's right there. And
Oh, good point. I see. Lead's below the stairs.
oh! Don't ever forget about the stairs.
So this is. I'm glad you brought that up because these are the transition elements, correct?
Yes.
But there's some seepage. You know, the ground is kind of like wet, and the house begins to slip a little bit and slide. These count as trannies too. This little like group down here. So do you have to worry about that? No, because if they want you to consider that it has a charge different than that in the column that it would normally be in, they'll give you a Roman numeral.
Okay.
So if they give you a Roman numeral, don't ask questions, don't become philosophical, salute, say yes sir, and follow orders.
Okay.
Will they always give you a Roman numeral?
Yes.
Okay.
If they don't, then it's just whatever's in the column. But for that case, where lead happens to be in a column that actually has a standard charge,
Okay, so
but
for the
but for these guys over here, for the real trannies, there is no set charge at all.
okay, so
So they always have to give you a Roman numeral for any of these, and if they want you to use one of these down here below the stairs, they also have to give you a Roman numeral. The exception is aluminum, which you're supposed to know is +2 because it's actually above the stairs. If you look at it, is
So
aluminum
aluminum
above
is
the? I
part
mean,
of the
aluminum is below the
stairs.
stairs, right? Yes,
Below.
it's just below the stairs, but it's so close that it counts as part of the +3 column.
So it is part of the stairs then.
Yeah. So are we okay with a little bit of gray area there? I'm glad Jessica brought that up. There's a little bit of gray area there, but we can handle it, right?
Is it the same thing with tin and?
No, it's not. It's just aluminum that's +3.
Just aluminum. So
So tin they'll give you a room
gallium
for.
and indium
Yeah.
and tin and lead are all transition metals.
Unless, for example, sometimes for gallium, let's say that they didn't tell you didn't tell you a Roman numeral for gallium. What if they said gallium fluoride?
Would I just assume that
plus
gallium.
Yeah, you have to assume that whatever's in the column is what it's going to be.
Okay.
But that won't come up, trust me on that, okay? This,
Okay.
it's a real good question, but it's an exception to the pattern, so it won't come up. All right, so we're okay with this. And where was I? Taylor was going to flip-flop and drop, right?